Hi, welcome back to Python programming from beginners to programmers. So at this point in our discussion about data analytics using Python's pandas library, we have come this far into being able to slice and dice the entire huge data frame, to compose from smaller data frames into larger data frames, to be able to programmatically change content based on the content's nature, to be able to filter off unnecessary data, to be able to extract out based on the content, based on the column values, based on the index values, and also to detect error and get rid of unwanted major source of irritation, data irritation, and noise and type errors and all that. So we are very versatile at this point. However, we have not even started on the statistical calculations. And in this video, we would like to move head on towards that topic. So we'll want to talk about how to perform computations. Fortunately, performing statistical analysis and calculations is as easy and as similar as slicing and dicing the parts in the data frame. So the major statistical functions are quite supported. For example, when we want to perform adding up of all the numbers in a column, in a row, across the entire data frame and all that, we can easily just summon data frame dot sum, that's all. And I think we have seen that before, right? In our discussion of error detection and handling. So if it's the normal integers, we will sum them up. So in this case, for example, we will perform dot sum, and the dot sum is understood to be a column sum, and therefore the columns are retained, and the across the rows, each column is going to be added up with all the contents in the data cells. So, for example, in column B, C, and D, we end up having integer totals of the various integers across the rows in each column vertically. Yeah? And something strange happens here when the column is a string. And because, in Python, plus makes sense, right? So if a string A is to be added to a string BC, you end up getting a string of ABC. So, like it or not, when your column A is a string, all right, we basically made a copy of a df6, which is a bunch of integers, and then specifically change A to a bunch of text characters. So when we have strings and we ask pandas to add across the various string cells, they behave like Python's string addition. So they get chained up, concatenated up, and we end up getting a string of xyx, zyxx across like this. So I just kind of shrink the string into this tiny little string here, but the idea is that it contains the uh, concatenation of all the strings across the cells in column A. But if we need a row sum instead of column sum, that means we're going to perform sum adding horizontally instead of vertically. We just insert axis equals to 1, right? So this is pretty um, standard in the kind of activation mechanisms. Just insert axis equals to 1 across most of the similarly uh, 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 categorized pandas functions. So in this case, almost all these statistical functions, so long as you want column kind of calculations, then just run it like dot sum or dot median or dot standard deviation std or dot max dot min, right? And if you like to be basing the calculation on row wise kind of performance, then you just insert axis equals to 1. So it's very this standard nature of communicating with pandas what we want makes it very easy, because while you may find it a little bit of a learning curve now, it kind of like have to memorize this, but after you get over it, it is like very very scalable, very much of the sense of learn once and use in many places, and so it is very productive in that sense. So axis equals to 1 row wise. So when we try this out with dot sum, we get 3 plus 6 plus 8, 14 plus 3, so 17. Now notice that x, the string x in column A gets left out. A bit like the behavior of Excel. Now I know some of you are thinking like, of course, shouldn't it be the case, right? And some of you, however, might be thinking, well, I thought string plus string is going to be a concatenation, so we should concatenate x with 17 so that we can x 17, right? Fortunately, that is not the case, um, or unfortunately, because we are having string plus int, and that actually shouldn't make sense. But what is really fortunate is that pandas doesn't just keep complaining. No, column A is string, so I'm not going to be able to perform anything at all. So instead of giving this very nice results that I suspect will fit in many cases, instead of giving this, pandas gives an error, and that will be quite an irritation, right? Because really we just want to add up anything that's numerical. So can you, pandas, please skip over anything that's non-numerical and then just quietly add them all up? And fortunately, that's exactly what pandas does. So the behavior is very much like Excel. That if you sort of selected row number 0 here and say sum this entire bunch of values, and Excel will not flag an error. Instead, it will skip over X and quietly add up 368 and return 17. So that's nice, and this is what pandas does. Okay, so adding across. And if we need correlation, then what pandas does is that it will again skip anything that is non-computable, non-numerical. So column A will be dropped out, and all the columns will be cross-correlated with all the other columns. So B will correlate with B, correlate with C, correlate with D, and so on. So what we get will be a sort of a new data frame like this, where we have column labels that are numerical and the index labels that will be also the same as column labels. So it'll be a square matrix by definition, right? And of course, by definition of the correlation, anything that correlates with itself, you will get back 1, right? So you will get 1 across the diagonal, and that is always going to come out like that if you put a dot core, C-O-R-R. So by just specifying dot core without anything, pandas will correlate everything that's numerical and skip over those that cannot be computed, which is very nice because then it saves us a lot of trouble trying to say, you know what, skip the name part, skip the address part, skip the postal code because we don't want to correlate something that's not really numerical, and so on. So as long as it's string, pandas will just skip over. So that's nice. And one way to detect any uh, significant correlation is to check for the largest correlation value, right? So here, for example, ignoring negative uh, correlation, suppose we like to check for any positive correlation, then we can eyeball it. But again, as I keep repeating across my videos, the whole point in trying to do all these calculations is not to perform such calculations over simple examples that like what I'm giving now. For obvious reasons, I'm not going to inundate you with a lot of data, and neither is that the whole point of learning. But rather, we need to imagine that when we apply our skills here to huge data frames, 5,000 rows and 3,000 columns, then we really don't want to eyeball a huge correlation matrix like that. So what we want is a programmatic way to detect it. And we ask the question, which column or row is significant, right? Is having huge correlation value. And the column and rows typically will be things like, for example, income, right? Number of cigarettes smoked per day, education level. We can sort of put the number of years of studies, right, in formal education, as a measure of how much education that person has. So all these numerical measurements will correlate with every other. And we are interested in finding which factor, right, which source of measurement kind of correlates with another interested measurement. So, for example, is it true that the more number of years of formal education one has, the higher is the average income, right? So in social studies, in business, in even science, definitely in science, we like to see such connection. Or connection is a more uh, informal description, but the right word is correlation. But from correlation, which has a specific technical meaning like this calculation here, we can then project and guess that, yeah, because having more correlation, because the correlation is strong, therefore having higher number of years of education will result in higher average income level, if of course it's a positive correlation, right? So oftentimes we like to find out which factor, which measurement, therefore which column label exhibits large correlation value.